All right, and we're back after a nifty experiment that had some unintended side effects. We're back to magnetic induction to be able to explain why what you just saw happened the way you did in a little bit more detailed level. So our goal is to understand magnetic induction. Our objectives were to understand how to induce a current. We're going to understand how to induce a magnetic field and how this allows us to generate alternating current, which is how most of the electricity in the United States is generated, although the energy source differs from source to source. And we'll learn a bit more about transformers and fortify why they work and why they only work for alternating current and do not work for direct current. By the way, if you're watching this lecture a little early, this lecture will not be on exam 3, it'll be on the final exam. The previous lecture on currents and circuits, that will be the last lecture on exam 3. This will be on the final exam. All right, so there's some ways to have fun with magnetic fields. The first involves changing a magnetic field in terms of magnitude, like we did here. The other involves spinning a wire in a magnetic field. So you keep the magnetic field steady and you spin your object. So you keep the object steady, change the magnetic field, or you can keep the magnetic field steady and rotate your object. So if you have a magnetic field that changes, magnetic fields are force barriers to charged particles. As the magnetic field gets bigger and smaller, those magnetic fields expand and contract. Field lines expand and contract. As they do so, they push charged particles around, namely electrons. That generates a current in any object that is ferromagnetic, such as my iron pot there, and will generate a current, or copper. It doesn't work for aluminum. So a changing magnetic field generates an electric current. This current is called an induced current, thus induction. So a magnet traveling through a looped wire is a way to change your magnetic field. That will induce a current in the loop of wire. The amount of current depends on two things: the rate of change in the magnetic field, in other words, how fast you move the magnet, or in this case, how quickly do I fluctuate the magnetic field, and by how much, in the area of the loop. The bigger the loop, the bigger the voltage, the bigger the current. And that's going to lead us to transformers, because we have loops of equal size. But it turns out it works both ways. Not only does a changing magnetic field induce a current, but currents also induce a magnetic field. Wow. So that means that a current will change the magnetic field, to induce a current. And so clearly you cannot choose the can of chili in front of me. Because it's still kind of warm. You're probably wondering what we'll do, that's fine. I'll let you figure it out. So, again, if you change your magnetic field, that induces a current. That current induces a magnetic field, which induces another current. But it decreases in terms of value until it gets to zero. So you have induced current and induced magnetic fields. Now the induced magnetic fields are going to oppose the change of the actual magnetic field. So if your magnetic field increases, you'll have a negative induced magnetic field, but it'll be a very weak field. So it won't quite work. It's like trying to suppress the status quo. When someone changes the status quo induces a counter change. It tries to counter the change, although it fails miserably because it's much weaker than the actual change. Not the best analogy, but you get the idea. So each loop, if I have multiple loops, each loop gets its own current and its own voltage. If I have 10 loops, I get 10 currents, and if they're the same size of loops, I get the same amount of current in each loop. And the same voltage in each loop. And that's why for transformers, the voltage on each side is just determined by the number of loops, because each of the loops are about the same, are usually the same size. And so that's why the voltage works the way it does. Each loop has a certain amount of voltage because of induction. Now please note that means that this only works for alternating currents, because direct currents will not generate a magnetic field, which will not generate induced current on the other side. And so transformers only work for alternating current, because they're not actually, loops aren't actually touching. So direct current sees a transformer as an infinite resistor. Power doesn't go through. Alternating current, it goes through. And so that's why, part of the reason why we use alternating current is that way we can ramp up the voltage really high, transmit it very efficiently, and then ramp it back down. You cannot do that with direct current. And I think I just covered this. You can read it real quick. Just a quick note, if you build something near either changing magnetic field or current, you have to watch out for induced currents and induced magnetic fields. So be sure to have resistance. Otherwise, those induced currents could create a short and could basically burn down whatever you're building. So be careful. And I cover this transformers again. Each loop has the same voltage because you have a loop and a changing magnetic field. All right, so how do we generate an alternating current? Well, instead of changing the magnetic field like we did for this device here, we have magnets set in place, and we rotate a loop of wire inside that magnetic field. Now, magnetic fields have directions. They point somewhere. So if I have a loop and I spin the loop around, the loop sees the magnetic field change. Even though the magnetic field is in place, it sees it go from positive to negative to zero, or positive to zero to negative to zero to positive as a sine wave. And as a result, the current generated on the loop is also a sine wave. Sometimes it's going to be positive when it sees the magnetic field increasing, and sometimes the current will be negative when it sees the current magnetic field decreasing effectively. And so you get a current that alternates from positive to negative and positive and negative. That's how the alternating current is generated. 99.999% of all electricity produced in the United States and almost worldwide is produced as alternating current. Now, the difference between different forms of electricity, different sources of electricity, is the energy source behind spinning the wire. Spinning the wire in a magnetic field is not free. It takes energy to do that. In fact, the energy you get out as electricity is the energy you have to put into the wire minus efficiencies. So you actually lose a little bit of energy doing that. So it's not free. So it's not an infinite energy machine just spinning the wire in a magnetic field, because it takes energy to spin that wire and keep spinning that wire, because the magnetic field will try to slow down the spin of that wire as it creates the current. So the different energy sources, fossil fuels, burn the fossil fuel and use that heat energy to boil water. That water is put through a turbine, narrowed to make it go faster. The water, then the steam hits the wire, hits an object that rotates. That rotating object then rotates the wire in the magnetic field, which generates the electricity. For wind, you spin the windmill. That windmill spins the wire, which generates the electricity. For hydroelectric, the water goes from high to low. As it's falling, it spins the turbine, which spins the wire, which generates the electricity. So all of the different ways of producing electricity, except for solar, produce alternate current. Even nuclear works almost the same way as fossil fuels does. It just does it on a bigger scale. It heats up the water to steam, and then the steam turns the turbine, which generates the electricity. It's just a different energy source for heating up the water, which is why it's very inefficient, because the steam carries energy away, And so most of the energy doesn't go to producing electricity, it goes to producing steam. And that's true for fossil fuels as well. Solar is the only one that produces direct current, and it does that through a process called the photoelectric effect, which was the discovery which gave a Nobel Prize to its discoverer. It was the only Nobel Prize won by this particular scientist, which is very strange because he came up with very great things you would think he would win Nobel Prizes for, but that's the only thing he won the Nobel Prize for. The scientist's name, Albert Einstein. And it works by a photon hits a piece of metal and knocks off an electron. The metal does tax a portion of the energy, so you don't get all the energy of the electron, but it shoots off an electron and that generates your electric current. And that's how you get energy from solar power. It's also the method by which you can see this image on YouTube, this video on YouTube, because my camcorder is actually using the photoelectric effect in its CCD to produce this effect, to produce the image, and count the number of photons of different energies to give you some semblance of color, etc. So that works for digital photography as well. You can thank Einstein. Unless you really hate digital photography, then you can blame Einstein. All right. And I think I covered all this. So, kind of a short lecture. We've learned about induction both from induced magnetic fields and induced magnetic currents. Well, induced fields and induced currents. We've now understand hopefully why transformers work and why they only work for AC. And we've learned how to create AC circuits and now understand how most of the electricity in the United States is produced. All right, so that's all for this week. I will see you next week when we'll have 2 lectures. 27, 28, or 29. I don't remember the numbers off the top of my head. Those are the last 2 lectures for the semester. And then we'll have the final exam. So we're on the home stretch, ladies and gentlemen.